So in Module 10, we get into advanced concurrency concepts. This takes us from that introductory discussion of scanning the LEDs and polling the switches up through to using a real-time operating system with a preemptive scheduler. So in this module, we look at preemptive multitasking concepts and then get into the basics of a real-time operating system, and we use free RTOS as an example. And there are several demonstrations that show concepts associated with tasks. Then we look into how to build a multitasking system using free RTOS. We look at how to trigger tasks, how to put time delays within them, how to synchronize with other tasks, how to send messages, how to share data and resources safely, and how to use interrupts. And finally, there's a hands-on exercise in which the students will add code to a starter application in order to use the features provided here. So we start off with our review of our simple LED scanner and switch polling example, which has poor responsiveness. The switch presses here are ignored. They're only recognized down here. And remember, we started with this run to completion task model and built upon it. We looked at how to use finite state machines so that each task takes less time to execute. And we saw how that reduced execution time increases the polling frequency, so we get a smaller delay. We also looked at the fact that we were still wasting time with busy waiting in the finite state machine. So we next looked at how to improve the performance by connecting the switches to interrupts. And pressing a switch triggers an interrupt service routine, which detects that the switch has been pressed or released. And this significantly reduces the delay between pressing a switch and changing the LED lighting pattern. We got much better responsiveness with the switch ISR. There's still this busy waiting time within the scan LEDs. So the CPU is wasting time just burning through a loop. So we looked at how to improve that by using a hardware timer. And with this, the hardware timer triggers an interrupt that will advance the LED scanner state machine to the next state. As a result, we end up with code that is much more efficient. Code only runs when it's really needed. So the ISR code only runs when the switch is pressed or released. So here, ISR switch changed. We have an interrupt triggered on the switch press and another triggered on the interrupt on the switch release. So that's much more efficient. And similarly, this LED scan code is only running when the code needs to go to the next state. So these are highly efficient interrupt service routines. That introduces the students to the concepts of preemptible tasks, and we show why these are important and why they help design systems. We then introduce the concepts of a preemptive scheduler that allows tasks to be in several states, ready, running, or blocked, and we discuss how the scheduler moves the tasks between those states. We have an example of what actually happens in a program with preemption. We can see there's an idle task running, and then a scheduler starts running when it determines something needs to happen, and anyhow, we see the interplay of all these different pieces of the program. In the end, we end up with a cleanly executing system that shares the processor's time efficiently. We look into how task preemption works. We look at how context switching works, how we save the CPU registers into memory, and we have separate data for the separate tasks. So then we get into applying these concepts of preemption and a scheduler to a real-time operating system. And we discuss the pros and cons of using an RTOS. And then we take a look at the free RTOS, which is used in this lab. We look at concepts of scheduler ticks, task priorities, task structures. So in free RTOS, a task consists of a root function, and within that root function, we have an infinite loop, which runs indefinitely, and it has some kind of call to the operating system that will block to allow other lower priority tasks to run. Higher priority tasks could always preempt this task, but lower priority tasks need to get a chance to run as well. So we have something such as task delay or some other blocking function that's going to yield the processor so lower priority tasks can run. We look at how to create a task and how to start up the system. There's the xTaskCreate function that we use to tell the scheduler where each task is and other configuration information. And then we start running the scheduler. We look at the scan LED application implemented in FreeRTOS, and we try it out. This is one of the demonstrations, and we can see the code is pretty straightforward. Here's polling switches. We check to see if the switches are pressed. We update the variables, and then we call this vTask delay function that waits for some time until it's time to read the switches again. The scan LEDs function looks like this. It's nicely self-contained, and here we just have an infinite loop, and within this we're checking to see if the LEDs should be blanked or not, and if they shouldn't be blanked, then we can go ahead and change the first LED. Next, instead of doing a busy wait call as we did originally, or instead of using a hardware timer, we're going to take advantage of the RTOS's built-in timer functions. So vTask delay is a function that will delay this task until this amount of time has gone by. So by using this RTOS delay support, it makes it much easier to write a clean function. And the main function is quite straightforward. We create the two tasks after setting up the hardware, and then we start the scheduler. And there's a demonstration program which scans the LEDs and reads the switches and works very efficiently. Then we get into a section of the module where we focus on building a multitasking application. And we provide the big picture of how to design an application. And we show how to break the application into separate tasks and then analyze the tasks to find the interactions between them. So there may be issues of task triggering. When does a task run? Synchronization. Should this task run after another task runs? How do we send information through messages with one-way data flow? How do we share data and share resources? We then apply the appropriate RTOS primitive operations to these intertask interactions. So we show how to protect a shared resource using a mutex. We show how to use semaphores to signal between tasks. We show how to use queues to pass multiple messages between tasks. So in triggering tasks, we consider what should the task wait for? Should we have a time-triggered or an event-triggered task? So we can start defining the application characteristics this way. We look at how we can delay a task for a certain amount of time or delay it until a certain time arrives. Both of these are necessary. We look at how to use event triggering so that we can make a task run when a certain event occurs, and that event is signaled by another task. And we look at examples of using semaphores. So we have an example where pressing the switch is going to cause the pull switches task to signal a semaphore that the scan LEDs task is going to read. So every time you press the switch, the LEDs scan once. So this is an example in the demonstration code. We also look at message queues and how they're different from semaphores. So a semaphore is essentially an event. Something happened. A message is an event plus data. This happened. So we need to pass that additional information, and we use a message for that in FreeRTOS. And we have a queue of messages so that we can support accumulated work. If it takes some time before this task can run, we can accumulate multiple requests in the queue and make sure we don't lose any of them before task B can execute. We look at how to use message queues in FreeRTOS. And then we get to preemption and race conditions. This is a fun part because we have an application that makes it very clear what the problems with data race conditions are. We have two tasks that are both trying to update the OLED display on the basic I/O shield expansion on the Wi-Fi board. If one task starts updating the OLED and then it gets preempted by task 2 and task 2 updates it, and then task 2 keeps running. Eventually it stops, it blocks. Task 1 resumes executing. We end up with this horrible jittery display that is really bad. So here we see an example of the OLED display being updated by multiple tasks. So the free RTOS real-time operating system is running, and we have several tasks that are trying to update the display. And you can see it keeps bouncing around and jittering. There's garbage coming in because the tasks interrupt each other as they update the display. With this motivation, we can explain different solutions for how to address this. We could go with a very heavyweight elimination of all preemption. Don't let any tasks preempt each other. And we see that this delays all higher priority tasks when they don't necessarily have to be delayed. We then look at some better solutions. Maybe we just don't let the tasks which might use the OLED preempt each other. And then an even better solution, which allows tasks to preempt each other, but if they need to use the OLED display, then they have to take turns. So this is a finer grain approach, but it shows that the response time for the high priority task gets reduced significantly, and even the medium priority tasks responsiveness gets delayed, that gets reduced. And finally, the lowest priority task, that has longest delay, but that's fine. That's why we gave it the lowest priority. It's able to handle those delays. So we have this framework to build on to discuss with the students how to design the systems. So we discuss how mutexes work. We then look at how to use interrupts in FreeRTOS. We look at both high-level design goals, such as making the interrupt service routine as short as possible, as well as how to actually implement the ISR in the code. We look at structuring the work within the application. So how can we defer as much work to a task as possible? Well, maybe we need to buffer the data with a queue. So a peripheral indicates that it has data ready. The interrupt service routine runs in response to that, grabs the data as soon as possible, puts it in the queue, and then it returns, allowing something else to run. Later on, the task can use that data. A peripheral may signal that an event has occurred, in which case the interrupt service routine will set a semaphore to tell the task, hey, this event has happened, and that task can then signal other tasks if needed. So we have different approaches here. The lab exercise for this module starts with the demonstration program that had the bad display, so the jittering display with multiple tasks trying to update the display and interfering, preempting each other. So in this lab, students are going to learn how to use semaphores, mutexes, and queues and interrupt service routines in order to tie together the separate tasks in the system. So in this system, we have a couple of tasks that just write updating, incrementing numbers to the display. We have serial communications with the PC. Sending text through the serial port will result in this task running and information being displayed. There's also a clock task that tracks what time it is, and it sends information out the UART and also updates the display. And we see how to use the operating system resources, the primitives, in order to make everything work correctly. So we use a mutex to protect the OLED. We use a semaphore so that task 1 can trigger task 2. We use message queues that hold information from the clock task to be sent out the serial port, and also to receive information coming in the serial port to go to the serial input task. And finally, we have 2 interrupt service routines to perform the UART interfacing for the communication. So this lab gives a nice hands-on demonstration of how you use these pieces. And is a nice way of wrapping up the discussions of concurrency that we have throughout this course, starting from the very beginning where we have this cyclic superloop without any preemption with static scheduling, and we see how things progress from the beginning to this point. So at the end, the students are familiar with these concepts and are able to apply them.